sector in consumer goods. We're also supporting Unilever, Sephora, and media. We also work with 21st Century Fox and Ubisoft. So some of the key drivers of operationalizing AI. The first driver is inclusive. The transformation of AI must include all profiles. Collaboration across the organization is critical and enables upskilling initiatives. So in this case, people, coders, and clickers will be able to work faster and smarter together due to this collaboration. The second driver is responsible. The transformation of AI must withstand a long-term objective of change of the organization. And responsible AI considers accountability, governability, and sustainability, which we're going to also touch base a little bit later in the presentation. The third driver is productionalize. The transformation of AI must allow the benefits of AI to be pervasive across the organization, from self-service analytics to full-scale operationalization. So with respect to that, let's look at how to assess a maturity level of an organization. There are two dimensions for really data maturity. The first one is inclusive data science, where you basically have no data silos, no team silos, because the environment is collaborative and you also have full employee engagement. And the second one is operationalized AI, where you have a short time to get to operationalization. What that means is in the beginning, you have big data starting at day 0, where machine learning is basically for specialists and ad hoc analytics, and also it's a siloed approach. From there, the next step is initialization, where you can demonstrate value. Then we go into impact, where you can deliver business value in operations. And then fourth, we go into acceleration, where you definitely get to structure, execution, and self-service. From there, we'll then get into systemization, where we have full alignment of data, organization, and processes. And then finally, we have what we call enterprise AI. When it comes to data and how it's influencing an organization, data is basically influenced from what we've been able to detail into 4 different categories. The first one is really for data scientists and engineers, and they have about 0.5% and 1% of ownership in that influence. Data scientists are building and integrating the very first building blocks for AI in the enterprise. The second stage of influence is then advanced analysts. They're the ones that are performing cutting edge analytics on the data, and they're tackling non-standard data and brand new needs from the business itself. The third influence is then analysts, and they're the ones that perform regular analytics tasks that need to be augmented by AI with strong control and understanding. That's about 10 to 15% of that influence. And finally, the last percentage of influence is 80 to 85%, and that belongs to really everyone else in the organization. They do not interact directly with AI, but they do benefit from AI as it's directly integrated into the business systems itself. But we've all read about the articles of AI. In this case, from the New York Times, we have AI could worsen health disparities. In a health system riddled with inequity, we risk making dangerous bias automated and invisible. We need to be very careful of that, as it's been happening before and it continues to still happen in the age of AI and in the realm of AI. The second article here that we have is MIT Technology Review, where we have AI sending people to jail and getting it wrong. AI has been making a lot of biased decisions, especially when it comes to gender, when it comes to race, and when it comes to age groups. You have to be very careful with that. Then the third article that we have here is from Berkeley News, where we have mortgage algorithms that perpetuate racial bias in lending, the study finds. We've seen this as well, where perhaps, for instance, you might have specific applicants that might have a specific salary, they have a specific credit score, but then again, gender can be an issue, race can be an issue, and then even the age groups can be an issue as well. So what that means is we need to consider responsible AI. And responsible AI is the idea of developing machine learning systems that are accountable, sustainable, and governable. That is, that they do what they're supposed to. They remain reliable over time, and they're well controlled and audible. The first critical components of responsible AI is governance. It's a must-have. So the must-have for governance is a view of which teams are using what data, how and which models, trust that the data is reliable and being collected in accordance with regulations, and a centralized understanding of which models are used for what business processes. This means we can't have shadow IT. And shadow IT is, for instance, if you have employees in an organization that are basically going into their own cloud environments like AWS, Azure, GCP, they're creating their own predictive models using the services that are available there, but they're not really considering the governance of how this AI is being controlled. For instance, no one's able to keep track of what they've been doing. There's no audit with respect to that type of information or the services that they've used in those kind of environments because they haven't informed their higher ups or even the IT department in this case. A second critical component is then sustainability. A must-have for that is infrastructure built for the future, leveraging the best technologies in a controlled way. It's reliable and continuous access data used to support current or future data projects. And there's a centralized place to monitor models in production with people accountable to their maintenance. The third component then is accountability. A must-have is assurance that data is used for AI projects that comes from compliant and unbiased data sources, as well as a collaborative approach to AI projects that ensures multiple checks and balances on potential model biases. We like to call this a human-centered approach, where basically we're providing people with the tools plus training to be aware of and then execute on all three components. Now, this is how it ties into Dataiku. Dataiku is a unified platform to bring together people, processes, and technology. It's a comprehensive and collaborative data science platform that enables teams of analysts, data scientists, engineers, and managers to effectively collaborate with each other, work with evolving technologies, and drive the AI projects from the design phase into production. As you can see here, Dataiku can be used for the Big Bang with respect to data, machine learning, ETL processes, data preparation, notebooks like Jupyter Notebook, data visualization, even different personas like a data miner, a business analyst, developer, or even a data scientist or data engineer. And then Dataiku represents an end-to-end solution, which is based on open source technologies and software. It's a platform for collaboration, and it's also focused on production-based products. So now let's talk seriously about powerful data and analytics. With regards to enterprise AI, there's always a fundamental challenge when it comes to software. In this case, I have three scenarios for you. The first one is when we're looking at siloed data. That means that data is most often there, but it's in many different forms and many different systems that need to be combined. The second challenge is siloed people. Success is not defined by having great business acumen or fantastic data skills or great analytic mindsets. You need them all together. The third challenge is then siloed processes. That means, like, for instance, you have teams that's focused on labs, IT, data, operations, or business. They all have their own processes, but all value delivery requires a bridging together into one platform if at all possible. So here's a solution overview for you. And this is really an end-to-end solution where you can consider data access to operationalize models. So as you can see here, an example, we have data management, we have machine learning, and we also have model deployment. Now let's consider different personas. In this case, the first persona we're going to consider is a business analyst. A business analyst's job is to first understand and prepare data. So in this case, they're going to look at the data management section. Next, then they're going to look at how can business modeling prototypes be created. They're going to then look at how to create machine learning models. After that, they're going to then look at model deployment. So in this scenario, they're going to look at how they can monitor results from a model that's been built. From that business analyst, then we go to a data scientist. With this persona, data scientist is going to be responsible for building plugins for business analysts. Plugins really are basically customized tools in which you can use inside of DSS, Data Science Studio for Dataiku, to basically build tools that can be used inside of your platform. And they're going to build these tools specifically for the business analysts. They're going to also consider building business monitoring dashboards for the business analysts. In this case, they can build a dashboard that can monitor these predictive models and, for instance, how these models are receiving specific scores or what responses they're getting for those specific scores that they're receiving. Are they meeting specific criteria like certain metrics? To continue the data scientist persona, we're then going to consider use for productivity and how to extend specific auto prep pipelines that have already been created with respect to data management. How does that data look like? Can we create charts from that data? Can we create basic statistics? And then from there, they're going to consider as a baseline how to optimize specific workflows that have already been created for use, for instance, by the business analyst or by themselves. The next persona we have is then a data engineer. Data engineer will learn how to optimize and speed visual pipelines that have already been written in DSS, as well as how to integrate these pipelines into then models that can be then deployed in specific API nodes or servers that can then handle API endpoints. And then lastly, and the last persona we have is the analytics leader. They're going to be able to understand, based on this visual pipeline, how this pipeline has been created and what to do with the actual pipeline based on how to actually monitor results and determine how to take specific actions based on the results that they see inside of a specific model that's being monitored specifically. Now, the two key modes of data innovation is first, self-service analytics, and second, operationalized ML. So when you look at the word operationalized ML, as you see here above, we create a new term called O16N. That just basically, if you consider Kubernetes, K8, if you've heard of that before, basically the 8 really represents the letters between the K and the S. In this scenario, we have 16. So the 16 represents the letters between O and N for the word operationalized. Now, O16N, we like to build robust solutions to business challenges. And so that means you can consider organizational driven challenges, focus challenges, also long-term challenges, fine integration, and then high value projects. And then with SSA, which stands for self-service analytics, we look for quick answers to unformulated questions. And these are questions that can come directly by the end users. They can be questions that are pervasive. We can consider agile, instantaneous questions as well, limited integration, and high volume of data as well. Now, we like to say that unleashing the full potential of enterprise AI isn't possible unless you really combine O16N plus SSA, which is what we call the AI acceleration formula. As you can see here, with O16N, we can ensure depth, and then with SSA, we can secure coverage. And a good way to do this is we can package tools for maximized reuse, we can consider centralized emergent key data, and then concrete data impact, which is building cultural momentum, as well as automated and repeatable processes. Basically, we're gonna build on the major global successes of all these. And then with SSA, we can look at how to build on the many local successes, for instance, pervasive data cultures, quick execution of small projects and free and advanced resources for larger ones, as well as emergence of high impact projects and data, and direct business data proximity. Yay, it goes around. Now, how can we future-proof your data effort and get results today and build for tomorrow? With Dataiku, you can leverage 4 different scenarios. In the first one, we can leverage existing skills and secure sustained availability. That means that you can take advantage of what you already use in your current environments and your current infrastructure like Python, SQL, Scala, Shiny, Bouquet, Cloudera, or R. You can then also use your current infrastructure and be ready for tomorrow's infrastructure, like for instance, using Docker for containers, NVIDIA for computation, Vertica and Teradata, as well as AWS, like AWS cloud providers, or GCP or Azure for computation or for creation of your infrastructure, as well as Cloudera. You can also maximize usage of most up-to-date technologies. Like for instance, if you're already using massive predictive libraries that take advantage, for instance, of like deep learning, for example, or NLP, you can take advantage of still continuing to use TensorFlow, Scikit-learn, Keras, Jupyter, and H2O. And lastly, you can extend based on current and future operation requirements. Like for instance, if you need to use specific data visualization tools, you can use DSS to export your current workflows or output data sets to be used as part of data visualization tools like Tableau, Alation, or Quaylic, or Esri. And here's just an example of a Dataiku DSS ecosystem and some integration touchpoints just to talk about. We have specific tools that we can use inside DSS. We call these recipes. The yellow ones are called visual, the orange ones are called code recipes, and then you also have the specific tools that you can, or services that you can use from other platforms, like Glue from AWS. You can also use Jupyter Notebooks inside of DSS if you want to write code, and then you can even integrate your current existing IDEs into the platform. As you can see here, you can use it to connect, explore, prepare, train, and deploy your models. And then if you want to send computation out, you can take advantage of using external resources or instances, in this case, with respect to the services you're already using, because DSS can be used as an orchestration tool to take advantage of that. So you can basically scale your computation for how you connect your data sets, for how you explore your data sets, and use them to continue to compute specific computations, like for instance, Kubernetes. You can take advantage of storing your data and preparing it as well. With respect to using Redshift as a data warehouse, you can also continue to train your data in instances like EC2, for example, on AWS. You can also train your model specifically and connect them with the SageMaker API, or you can also deploy your models into EMR, where you can then create your own specific types of clusters, as you see here as an option. And then you can also scale how you store your data as well with respect to the different cloud providers, like using S3 buckets, or also taking advantage of SQL databases, or even a data warehouse as well. Great, thank you for listening. And I would like to end with saying export Dataiku DSS for yourself. And if you can, please go to this link right here yourself, and then just go download a free trial. It is available for 14 days, where you can take advantage of having to learn how DSS works, and also take advantage of our academy that we have available in the community that's hosting that academy for you. But besides that, I would like to then introduce our speaker, Eugene Steinberg from Grid Dynamics.
Hello, everybody. Let me share my screen. Welcome to our webinar, and thank you, John, for introductions. Today, in our speech, we will be talking about deep learning-based product recommenders. My name is Eugene Steinberg. I'm technical fellow, founding engineer, and head of deep learning practice at Grid Dynamics. So first, a few words, very quick introduction of what Grid Dynamics is. So we are a data science and engineering services company. We've been around since 2006. We're about 1,500 people globally. We've been recognized by Forrester as a leader in the space of mid-size agile development service providers. We work very closely with about 20 plus Fortune 1000 companies. And what we do is we are known for helping those companies to perform a digital transformation using emerging technologies, which includes things like personalized search and recommendations. We more and more delve into the space of deep learning when we're using those recommendations, and we'll be talking about that today. It also deals with image analytics and computer vision, natural language processing, and many other kind of emerging fields which are redefined by the deep learning systems these days. So today we are going to talk about lessons which we learned while implementing product recommendations systems for several tier 1 online retailers. And mostly we will talk about collaborative filtering and limitations of traditional collaborative filtering approaches. We will speak about how deep learning models can help to fix some of the problems which are very common with collaborative filtering recommenders. And we will show you a live demo of data pipelines and algorithms which are working on top of Data IQ platform, which demonstrate some of the techniques which will be described here. So let's get into this. First of all, let's do a very quick refresher of what is collaborative filtering. It is a very popular technique in building machine learning driven recommenders. It was pioneered about a decade or maybe 2 decades ago by a variety of large e-commerce companies, including Netflix. And it all is driven by a very simple intuition. So how about we know something about a particular customer. We know about their preferences. We know that she liked particular items, in this case, movies. So how can we predict whenever she will like or not like a different movie? So the main idea is to recommend the movies which were liked by the people who share the same inherent preferences with this customer. And we believe that people who share similar tastes will like similar items. And that's the intuition behind collaborative filtering. So how to convert this intuition into something tangible by the machine learning algorithm? The answer is very simple. So we approach this problem as a problem of factorization of the matrices. So what does it mean? So first and foremost, we collect a very large matrix which basically captures the interactions between our customers and our items. In this case, as we see on the example of apparel e-commerce, we are collecting the information of what products customers purchased, what they viewed, and in general what they liked. So in this case, we are using an implicit signal to try to derive what is the level of interaction between a particular item and a particular customer. So after we collected this very large matrix, we are doing something which is called a matrix factorization. So matrix factorization is converting this large matrix into the product of 2 matrices. So one of the matrices is users buy something, and then something by item. So what is this something? This something is called latent user factors or latent item factors. And those are the mathematical vectors, which are typically not very large, which somehow describe the preferences of the users in terms of how they like particular style of the apparel, how they like particular style of the shoes, what is the general preferences in the size. But all this is wrapped internally into a vector. And it's pretty hard to interpret this vector, but still this vector is useful in order to predict what a particular customer will like or not like, because as it's shown here, we can predict the score which customer would give to the particular item by multiplying their user factors to the item factors as discovered by this model and predicting their score, and then sorting by the score, we can start making recommendations. There are many algorithms developed and being still developed, which are with different kind of speed and robustness, performance matrix factorization. There are many extensions to that, like alternating least squares is one of them, factorization machines, stochastic gradient descents. There are many kind of different useful libraries which we can use to do this kind of recommendations. However, if we look very closely, so if we look at very closely at this, oh, there's some issue with my slides. So if you look very closely at shortcomings of traditional collaborative filtering, they have mainly 4 main kind of problems which we have to take into account when we are thinking about dealing with those systems. First, usually those collaborative filtering recommenders are working on the level of ID of the customers and the IDs of the products. We are completely unaware about the metadata which we have about products. And usually we have a lot of metadata. We have product images, we have different attributes and descriptions. And it's also unaware about the customer profile data. Customers are not just IDs. We have genders, we have age, we have like preferences, which are sometimes explicitly known. And the implementers of collaborating filtering approach are usually having difficulties understanding how to employ this information inside their model. But the most prominent problem with collaborative filtering is a problem of a cold start. Sometimes we just don't have enough information about the interaction of a particular product with a particular user. There are products which are unpopular. There are products which are new. And we don't just have an interaction information between this new product and the customers, and therefore our model is completely powerless to try to predict anything meaningful about these products. There is just not enough data. The same applies to the problem of the new customers. So what to do with this situation? Traditionally, people look at this and say, okay, like for popular products, we will still use collaborative filtering because there is enough information. But for unpopular products, we will use a different type of recommender, which is based on the content. And the content-based recommenders are a big class of recommenders which are trying to make recommendations mostly based on the similarities between the products. So it's a lookalike modeling between the products. And in modern world, this is done usually using deep learning models, because deep learning models can encode pretty much any information which is available about their customers and the products. It can encode their product images, and it can encode attributes, and then we can vectorize both images, attributes, long text descriptions which we have about the products, and place all those attributes, all this data into the vector, which is kind of, in this case, will be mapped to some point into the latent feature space. And then performing a nearest neighbor search in this space, we can get recommendations for our items based on the similarity. And there are a lot of ways to train the model to understand this kind of similarity. This way we can kind of produce this kind of recommendations. However, when we do this kind of recommendations, we start to lose the interesting structure of behavior-driven recommendations. People do not always buy products which are just similar to each other. They also, like the collaborative filtering has enough power to uncover a very interesting relationship between the products, complementary products, or products which frequently bought together because they serve the same kind of overall use case of a customer. And if you do a purely content-based recommender, we are losing this interesting latent hidden features which were uncovered by the collaborative filtering model. And we are focusing only on the surface kind of similarity of products by image or by attributes. So how about we try to combine the benefits of a both world? And this is what we call a hybrid recommender. So in this case, the main idea is that we can view a deep learning neural network as a universal approximator. It is a system which can be trained to predict anything based on our content data. And in this case, what we can do is we can train it to predict what would the collaborative filtering system say about a particular item. Where would it place it into its own collaborative filtering latent space? So we can train this system using the information which is coming from the highly popular products, and this way stretch this understanding to the low popular products. And this is how we will do it in our demo. So the main idea again is that we are taking the content of the image of the products, like images, descriptions, whatnot, encoded, and try to train the system to predict the same vectors which would be produced by the collaborative filtering model. Demo time. So let's try to look how it is, how this data pipeline can look like in real life in the Dataiku data platform. So this is the Dataiku data platform, and this is our project, which is called a Deep Recommender. And as a basis of this project, we took a very well-known data set, which is coming from Amazon, which captures the interactions between the Amazon products and Amazon customers. If we go to the Dataiku dashboard, we will be able to go to the thing which is called, let's open the dashboard, and let's start by basically looking at what data set we have at hand. So we have Amazon public data set. It has an ID of some reviewers. It has some information about overall rating which those customers are given to the particular products. And then also have a metadata which gives information about relationship between those products in terms of also viewed, also bought. And we can use, again, some functionality of Dataiku to perform exploratory data analysis, which will immediately show very well-known information that, of course, in general, the majority of the items are in the e-commerce catalog are not so popular and have not a lot of recommendations, or sorry, not a lot of interactions. We can show a lot of different charts here, which basically convey the same idea about the long tail of the not so popular products for which less than 10 interactions occur, and therefore it is very unlikely that a collaborative filtering system will be able to make sense out of it without any help of the additional information about the contents of these pictures. So we can also build a so-called data explorer, which allows you to kind of show some of the products and check what is frequently bought together or frequently put into the basket together or viewed together, which shows you, like in general, kind of helps to build your intuition about your data set and understand it in more details. So let's go back to our data flow, and this is pretty much the main screen with which majority of our work will happen. So we have our data set, which was downloaded from internet. So this one node here shows the reviews. We have a special step, which is like off-the-shelf .iq step, which is showing how we can pre-filter it, make a little bit of data preparation. So this is a handy because we can avoid writing unnecessary boilerplate code. So this is like standard thing. We are getting the data set out of it, and then we start to prepare the training data for our traditional collaborative filtering model. So this is like a small, you can have a small Python script here. You can also view it as a notebook, but in general, what it does, it does a simple transformation of the data and arrives at the very well known to all of us traditional data set for collaborative filtering, which has like user ID, item ID, and rating. And our job is to factor this matrix, factorize this matrix, and this is exactly what we are doing here. So this is a step which uses the traditional collaborative filtering libraries. In this case, we are using alternating square approach, which factorizes this matrix and arrives at the embeddings of the items and users, which we are storing in this particular folder. So far so good, and all this is pretty well known and a standard kind of operating procedure if you are building the collaborative filtering model. But what we are doing here is a little bit more interesting. We also have some metadata about our products. And we have this metadata for clothing, shoes, and jewelry. And what we are doing is that we are using this data to prepare a special data set for deep learning model. And in this data set, we will select all the popular products or semi-popular products, and we will use their embeddings in the ILS space as a training set to train our neural network to predict what vectors will ILS give to this particular model. Thus, we will try to create a recommender which is able to perform a collaborative filtering style recommendations for products which are not really popular. So in this model, we are training our deep learning model. And once the model is trained, we have the new embeddings for the unpopular products, which we can use instead of original embeddings. And we can use it to start making some recommendations. And to make some recommendations, we have a dashboard, and let's try to do some comparison. So as you can see, for unpopular items, we immediately see the difference because this is the anchor product, and this is the recommendations which are given by collaborative filtering. And those are recommendations which are given more with our DNN approach. And as you can see, with unpopular items, we can start like with high popular items. For high popular items, we typically have a very nice data about interactions, and both for collaborative filtering and deep learning approach, we are getting reasonably meaningful recommendations. For medium popular items, we see that the recommendations become sometimes more bizarre on the collaborative filtering side, while they are more consistent on the deep learning recommender. And for low popular items, it's very often, I'm just getting some random recommendations here that they are kind of pretty bizarre on the traditional collaborative filtering and more consistent on the deep learning approach, like here. So like here we have some costumes, we have some glasses. Of course, because deep learning model also tries to predict the collaborative filtering embeddings, it does not only works on the level of similar looking products, it also tries kind of to pick up some of the products which are brought together, but in general results look more consistent. So Data IQ platform allows you to also build it's like different data flows. So for example, in preparation of those visualizations, we used a different data flow, which mostly used variety of models from Data IQ, which helped you to create the split of the data and select some of the random products for recommendations, put it back into this flow. We also have, if we go back to the dashboards, one thing which comes very handy when you're exploring the results of your work is to have an embedding projector, which basically shows the different, it shows like where exactly in the multi-dimensional vector space your model places the products. So this is how you can kind of navigate it. You see that sometimes the products create an interesting clusters which can be exploited by your recommender. But sometimes, like for low popular items, you have pretty random places of those products in the multi-dimensional space, and usually it shows that your recommendations will not be so good. We can also look at the deep learning projections for the same low popular items. Those are embeddings which are created by our deep learning model, and we can see that in this case it's a bit more consistent, and we have a different way to represent the same data. We have here you also can have in the Data IQ platform you can have a variety of notebooks, and one of the notebooks is as you can see, like there are a bunch of notebooks. Some of them are preparing metadata for embedding projector, some are calculating metrics, some of them are like calculating different metrics, and this particular notebook is preparing the embedding calculators for single category, and it's very interesting to look at the embedding data here. So this is a chart which shows the position of the products based on the embeddings coming from traditional collaborative filtering, and here you can see that you have a good cluster of highly popular items. They cluster together, they kind of separated by different clicks here, and in general that means that you can start recommending them based on each other. But for low popular items you have this long tail of pretty strange kind of far-fetching places where those embeddings go, and this shows, and mostly it consists of the unpopular items, and as you can see for recommender it will be very hard to make meaningful recommendations. While on the deep learning recommender we have a better structure of the latent vector space, then we can make a better recommendations of both like popular items by unpopular items or unpopular items by popular items. So of course with Data IQ platform we also can have a kind of to deploy the recommendations to production. So here we have our code which wraps up our model. We can also run a sample query against it. So we can run test query. Then what else? So for Yeah, and one more thing is that, of course, it is useful to show a variety of technical metrics. So we can calculate the precision and recall on the model. So I have difficulty with my instance. Yeah, so this is the calculations of precision and recall of our model. And as you can see, there, even if you look at the purely technical metrics, the deep learning, the hybrid model is given a pretty significant uplift in the metrics compared to vanilla collaborative filtering. Of course, it is worth saying that nobody is using the vanilla collaborative filtering in production usually, because there are many techniques how you can enhance the collaborative filtering model to kind of start taking, like to cluster together some products or to split your training set in a particular ways. But even in these situations, you still will have a problem of a cold start, and you will have to deal with it somehow, and different companies are doing that different way. So we chose to use like a deep learning recommender for this case, and it was really kind of easy to train, and it gives pretty significant uplift even on the very simple model which we employed here. In reality, the model which we'll use will in this particular project, we used only the information from the images and product titles, but in reality, we'll also embed all the information which you have about the attributes, long descriptions, passes through some sentence encoding layers of your neural network, and that all will allow you to get into more meaningful embeddings for your data. So, yeah, as I said, we have that IQ allows us to create a bunch of web apps, and I already showed you the web apps which we used in our dashboard. So yeah, it looks like I showed everything which I wanted to show to you today. Maybe it's a good time to go for some questions. Please feel free to ask questions in the Q&A section. Hard to say whenever people have difficulties asking the questions or no questions, it was crystal clear. Again, yeah, there was a question. Yeah, now a question started to come. So the first question is coming, can we apply those techniques in customer retention context? Yes, I think that you can. You would rather kind of want to create both embeddings of the customers, and there are many interesting techniques how you can create completely separate embeddings of the customers using the natural language processing methods. We have a separate blog post about that. It's called Customer to Vec. But you also can mix in the features of your customers to basically to your collaborative filtering recommender results, and improve your performance. If you are dealing with a customer churn modeling, that is something which is definitely going to help, because your model will start to be more aware about the context and the about the features of known features of your customers. And the features can be explicit or can be mined from your customer behavior using customer to vec approach. So I encourage you to go to our blog and read about the customer to vec approach. So yeah, it's a very interesting question. how are using data on-prem or cloud integration. So in this particular case, we deployed our platform on Azure. Of course, like DataIQ allows you to deploy it in any cloud. It was pretty easy to deploy, and it didn't fail us. And we deployed it on Azure, and it was pretty smooth experience so far. And obviously, it can also be it can also be deployed in on-prem if you're looking for it. If you have, for example, security restrictions that you cannot expose your customers customer data to the public cloud. Can you elaborate on how you combine the metadata and collaborative filtering to generate the recommendations? Yes, of course, we can elaborate. So basically, the main idea again, probably have to share screen again. The main idea here is to build a recommender which can use a deep learning model, which uses things like convolutional neural networks or things like universal sentence embeddings to combine all the information which we know about our customers, or products. And then this model will start projecting this model to the same vector space, the same dimensional vector space as the traditional collaborative filtering model. And then what you can do is basically you're creating a loss in your deep learning model in such a way that it will start trying to optimize the distance between the embeddings, which are coming from the content analysis and which are coming from collaborative filtering analysis. And you're doing that for highly popular products, so you know that your collaborative filtering features are good. And while minimizing these embeddings through backpropagation, you are training your neural network to start predicting even for the products which it never saw, vectors which are very similar to what collaborative filtering models would say. So in some sense, you're distilling or stealing the knowledge from collaborative filtering model and applying it to the content-based recommender. So basically, you're making content-based recommender to look and feel like it is a collaborative filtering recommender. That's the main idea. Hopefully, I kind of managed to bring it about. Please give a use case for any energy or media company who are leveraging this solution. Kindly enlighten this your market go-to strategy as well. So this is again, we are using this solution in the retail and fintech environment. I can imagine that a similar approach can be used anywhere where collaborative filtering is currently used as a basis, for example, for the churn model for media company, or like for media company, it's obvious, like it's the same use case like with Netflix. If you have a particular item which you want to promote and you don't have enough collaboration, enough interaction about this item, you will not be able to make a good recommendation using just collaborative filtering. So this approach allows you to mix in the collaborative filtering and meta information about this particular media item so that you can make still a meaningful recommendation for cold start. So this particular solution is not is about as go for market. It's not like it's not a solution which we are selling to themselves, because we are a professional services company. We are coming in and we are helping our customers to build those kind of systems with our knowledge, and we are passing our knowledge to whoever is interested. Next question. You have talked about advantages of deep learning methods. Could you please provide a concrete example of what kind of DL method will be used? In this particular case, we used a combination of deep learning model. Hard to explain. I'm not sure I correctly understand the question, but in this case, we used the combination of convolutional neural network like ResNet 50 to extract the features from the images. We used the universal sentence encoder to extract features from product names. And that all we kind of combined in the same network, which was trained through a bunch of fully connected layers to predict embeddings which are coming from collaborative filtering. We can discuss it offline. I'm always available to give more details. You mentioned IBM as a technology partner at your website. Please mention how do you like IBM help in growing your presence? Is there any way you could like us to help? Okay, so apparently, yeah, this question comes from IBM. So let's connect offline and we can talk about that. That's very clever how you combine the metadata and collaborative filtering. Can you recommend a detailed case study or tutorial where you can follow the code for an example case? We have a blog post on our blog. You can look at it, and we are planning to kind of publish the code behind this demo soon. So watch our website or reach us separately. We can talk about that, and we can share our approach and code. Very interesting. Very interesting. How long it took to build the model? To build the model, it took like 1 day. To train the model, it took 4 hours or something like that. I mean, the main problem here is not to train the model. Sorry, not to kind of design the model, but to train it and iteratively kind of improve the architecture of the model to achieve better and better results with your recommendations. So yeah, so like the training of the model itself using the DataIQ platform took several hours at most, and we made a lot of improvements to speed up performance. So is it possible to know the statistical significance of the prediction? We calculated the precision and recall metrics, but we can obviously connect offline and talk about other kind of ways to make those predictions. In general, like precision and recall, and also judging from our practical experience based on the business metrics in retail, for example, like this kind of recommendations are really kind of improving the conversion rates. So it has like its merit. The question is, yeah, the concrete statistical significance, it was pretty hard to build on this synthetic case. For this demo, I obviously couldn't use any real customer data. So this is just a demonstration of the approach in general. Can you show the structure of your DNN? What's the output of your DNN during training? Is it the output of LS? Yeah, this is exactly the idea. The structure of DNN looks something like this. It's on a high level. So it has kind of description and then word pulled output. In reality, in this project, we used a different kind of recommender. And it also has visual features. And in simplest case, you can just use the recommendations, the features which are extracted by some pre-trained convolutional neural network. In real case, you would like to build your own and train your own visual feature extraction, depending on your particular domain. But this is how, in general, it looks like very simple neural network for this particular product. In reality, it may be much more sophisticated. And but yeah, in general, the deep learning model predicts the same dimensions as we have in the kind of collaborative filtering model. Do you have any metrics on how much your sales improve? Use the DL approach. Yes, we have, but we cannot share them on this audience. It's proprietary information of our customers. Can you? Yeah. Is it possible to know? Yeah, I think I answered. Oh, where is your blog? It's blog.griddynamics.com. So blog. So you're welcome to visit us. Any other questions before we wrap it up? Can we interact? Absolutely. Good. Yeah, people are saying that they're using the very similar approach, and it's very nice to see that we are not like the only ones who came up with this idea. So definitely encouraging. So anyway, I think we are kind of almost out of time. I really appreciate your interest. Please visit us at griddynamics.com. And we would like to see you guys on our next webinars. Appreciate your attention, and thank you very much.